This week, finally, I'm going to develop the mathematical theory of gravitational waves. We have all the foundations that we need mathematically. We have the Einstein field equations, and I have brought us to the point where we can do this rather quickly, and I hope reasonably clearly. And you will see then the mathematical justification for a number of the properties of gravitational waves that I asserted when I was using the PowerPoint presentation in the first week. Many of the details I'm going to leave as exercises for you. I think they're useful exercises, and you'll understand it better by doing them. And so I'll simply say that what the result is, and then in the exercise sketch for you how to go about proving it, and let you work it out for yourself. So that'll be in the homework that I make available to you after the Wednesday class. This week, as last week, I will not put the homework or the reading on the web until Wednesday night or Thursday morning, because I want to have done the Wednesday lecture before I do that. Okay, so we want to talk about gravitational waves, and to make it simple initially, I'm going to deal with weak gravitational waves propagating through flat space-time, or through a space-time that is flat aside from the space-time curvature produced by the gravitational wave. And I will then, in order to make the mathematical treatment easy, I will use a reference frame or coordinate system that, aside from the gravitational wave itself, if you were to ignore this very weak gravitational wave, a reference frame or coordinate system that is globally Lorentz. Or in other words, globally Minkowski coordinates. So that I have coordinates x alpha, that is t, x, y, and z. And in this coordinate system, the components of the metric are those of the flat metric. That is viewed as a matrix minus 1, plus 1, plus 1, plus 1 down the diagonals. Now, that's the nature of the coordinate system or reference frame in the absence of the gravitational waves. And the gravitational waves then we will think of as a field that lives in this flat space-time, that propagates in this flat space-time. And so the gravitational waves I'm going to describe mathematically by their Riemann curvature tensor, or by the components of the Riemann curvature tensor in this global Lorentz frame. It is was an exercise for you on the problem set that I put on the web for you last week, that you're working on now, to show that in this kind of a situation, this Riemann curvature tensor, or the components of the Riemann curvature tensor, satisfy the flat space wave equation. And so that the proof of that, as you see when you work through it, it follows from the Bianchi identities for the Riemann tensor and the vacuum Einstein field equations. And the conclusion is then that the flat space wave operator acting on the Riemann tensor, by which I mean eta mu nu, r alpha beta gamma delta, comma mu nu, where these are now partial derivatives in this in these Minkowski coordinates, that vanishes. I also ask you in the problem set to derive an analogous exact equation. This is only approximate in these circumstances. An analogous exact wave equation for the Riemann tensor when this is not a weak gravitational wave, but it is in vacuum. So it's just an arbitrary Riemann tensor in vacuum, and you'll discover that you have a wave equation for the Riemann tensor that is similar to this, but in curved space-time with some self-coupling of the Riemann tensor. And I'm going to use that exact wave equation for the Riemann tensor later on when I discuss nonlinear effects in gravitational wave propagation and generation, and later on when I discuss the geometric optics approximation for waves propagating through the Friedmann universe or some curved background space-time. For now, I want just this simple flat space, the simple wave equation that in the circumstance of a weak wave propagating through an otherwise flat space-time. Now, I want to then in particular look at the influence of a wave that is propagating like this, the influence on test particles through the equation of geodesic deviation. And for that purpose, I want to choose two test particles that are initially at rest with respect to each other. And they're at rest in this Lorentz frame. And I'm going to put one of them at the spatial origin. So if I draw then a space-time diagram, one of them sits here at the spatial origin, plotting t up, x and y out. One sits at the spatial origin, and because this is a freely falling test particle, and this is a Lorentz frame, it then will move along the time direction. It's initially at rest. And then the other particle is sitting out here some distance away with a separation vector Cj, which I will define to be purely spatial. And that Cj then is just equal to the coordinate location of this other test particle. And as the gravitational wave goes by, the gravitational wave will push these test particles around with respect to each other. And the fact that they push them around with respect to each other means that this is not really a global Lorentz frame. It can't be in the presence of the gravitational waves. It was only a global Lorentz frame in the absence of the gravitational waves. And so in discussing the test particle motion, I need to make a little more precise the nature of the coordinates that I'm using. So I have to then allow for the presence of the gravitational wave. And so I'm going to then make my coordinates be the local Lorentz frame of the particle at the origin. That's particle A, call it. And the other one is particle B. So it's the local Lorentz frame of particle A. And since it's the local Lorentz frame of particle A will remain then at rest in this coordinate system. That's basically the definition of a local Lorentz frame. It's the closest thing there is to a global Lorentz frame that's built on the world line of a freely falling particle. And there is some mathematical discussion of this, in fact, in the problem set, again, that I have given you for this week. Okay? And so there you will see a detailed discussion of local Lorentz frames in a particular example, and then some more general discussion. So the statement is that this local Lorentz frame, the physical meaning of it is that this particle A falls freely and carries with itself a lattice work of rods and clocks that are identical to the lattice work of rods and clocks that you would use in special relativity discussion to build a Lorentz frame. And so if I just go over and draw a spatial picture, here's particle A here. It's at the physical origin of this lattice work of rods and clocks. And it carries it along with itself as it falls freely, carrying the origin along with itself, attaching the lattice work to a set of inertial guidance gyroscopes so that the lattice work doesn't rotate, and keeping the lattice work and the clocks as keeping the clocks ideal in the lattice work as nearly rigid as is allowed by the space-time curvature that is encountered. And as is shown in the exercise that I'm giving to you, under those circumstances, this resulting local Lorentz frame of particle A will have the property that all along particle A's whirl line, the metric coefficients are the flat space metric coefficients plus something that is second order in the spatial distance from the origin. So all the way along this whirl line, the metric coefficients are precisely the flat space coefficients. You go off somewhere over here and you measure the spatial distance in this coordinate system as measured using the rods of this lattice work. That spatial distance is what I've denoted here by the vector x, the spatial vector x, absolute value squared, the spatial distance squared. G alpha beta is eta alpha beta plus something of order x squared. It's actually of order x squared divided by the radius of curvature of space-time, where the radius of curvature of space-time, or 1 over that, is basically the components of the Riemann curvature tensor in this local Lorentz frame, the characteristic magnitude of the components of the Riemann curvature tensor. This has dimensions of 1 over length squared when we set the speed of light equal to 1, as I generally do. So 1 over the radius of curvature of space-time squared is the magnitude of the Riemann tensor. And the statement then is that G alpha beta is eta alpha beta plus something that looks like the Riemann tensor times x squared. Okay. And so that is something that you actually will explore in the problem that I have assigned for this week, that I was in the problem set that I put on the web on Thursday. And then in this local Lorentz frame then, particle A remains always at rest by the way the local Lorentz frame is constructed, and particle B then, under geodesic deviation produced by the Riemann curvature, particle B must move back and forth so that the separation Cj changes with time. And the equation of geodesic deviation then says that, of course, the precise form in frame-independent coordinates is del u of c is equal to minus the Riemann curvature tensor. Leave the first slot empty. Put u in the second slot, c in the third slot, and u in the fourth slot. And it is rather straightforward then, and I think I also assigned this on the problem set, to verify that in this local Lorentz frame, the components of this equation simply reduce to a second time derivative, and it's a partial with respect to the coordinate time. Coordinate time, however, this is being evaluated along this whirl line, so coordinate time along this whirl line of particle A is the same as proper time of particle A, since particle A is the particle that has this four velocity u, and since particle A is at the origin of this local Lorentz frame, and at that origin the metric has the flat space form. And so coordinate time is the same as proper time, and the equation of geodesic deviation reduces to a second time derivative, ordinary partial time derivative of Cj is equal to then minus Rj hand side. This slot was empty, so this index j is the same as that index j. U is the four velocity of particle A, and this is a particle that's at rest in a Lorentz frame, where the metric along its whirl line is precisely the flat metric. But U has as its only component, U0 up is equal to 1. The spatial components vanish. So that's why this becomes a J0. The third slot is the slot into which we have put C. And so C is contracted in there, But I'm only contracting the spatial part of Xi because Xi has no temporal part. I've chosen Xi in such a way that it has no temporal part. And then again, a 0 here for the same reason as before, that I've put the 4 velocity of particle A into the fourth slot. So this is the coordinate realization, or the component realization of the equation of geodesic deviation in this circumstance. And it is also, I remind you, the equation that we used to compare to the Newtonian equation for the tidal forces in order to discover that Rj0k0 is really just the Newtonian tidal force, or the double gradient of the Newtonian potential in a Newtonian situation. So last week when I talked about the Einstein field equations, we needed a connection to the Newtonian limit. And I used this equation, comparing it to the tidal force equation in Newtonian theory, to get out that connection as a foundation for the Einstein field equations. Okay, so this is then the equation of geodesic deviation under these circumstances, but because the components of Xi are just the coordinates of particle B, in place of Cj, I can just put the coordinate. But I want to break the coordinates of particle B up into two parts. I want to write this as xj, let me call it 0 for unperturbed, plus delta xj, the change in coordinate of that particle induced by the passing gravitational wave. And if I do that, then this change is very small because the gravitational wave is assumed to be weak. And so that means that over here where I have Xk, I can approximate that just by the unperturbed coordinate location of the particle. And over here, the only thing that changes is the perturbation of the coordinate location. So that's delta xj. So the equation of geodesic deviation then reduces to a second time derivative of the change in the particle's location. That's location of particle B now, the one that is wiggling, is equal to minus Rj0k0 times the unperturbed location of particle B. I'm going to make notation a little bit easier as I go along now by recalling that this is the component in the local Lorentz frame at this location where the metric coefficients are precisely the flat space coefficients. And so I can raise and lower spatial indices freely. Components don't change. If I raise and lower temporal indices, I flip a sign. Okay. And so I'm going to rewrite this as minus R down J0K0 xk unperturbed. So that then is the form I want to use for the equation of geodesic deviation. Now, I now want to tell you a theorem, a physicist's theorem, a mathematician's remark. They only use theorem for very, very big things. And that is that in this local Lorentz frame that I have been using, that at origin, or thinking about it equally well, in the global Lorentz frame of the background spacetime through which the wave is propagating, all other components of the Riemann tensor are determined fully by the components R, J, 0, K, 0. This is true for a gravitational wave. For this case of a weak gravitational wave, this is true. It is not true in general, not at all true in general. But for the weak case of a gravitational wave, this is true. Again, proving that is going to be an exercise now. In the problem set that I will give to you this Thursday. And so that means that there must be some way to compute the other components, and you will derive, in fact, in your proof, what they are in terms of this. Your derivation will just follow from the symmetries of the Riemann tensor plus the Bianchi identities in the vacuum Einstein field equations. So there is a way to go from these guys to all of them. I remind you that in general, there are 20 independent components. And as we will see in a few minutes, here, in fact, although it looks like there may be more, it looks like this is something that is a symmetric 3 by 3 matrix, if you want to think about it as a matrix. Because J can go over X, Y, Z, and K can go over X, Y, Z, and it's symmetric under interchange of these pairs. So symmetric 3 by 3 suggests that there really ought to be 6 independent components. However, as we will see in a few minutes, there are only 2 independent components. Again, by virtue of the Einstein field equations and the Bianchi identities, it turns out only 2. In other theories of gravity, you can have additional independent components. This statement that for weak gravitational waves, all other components are determined by Rj0, K0. That's true whenever the Riemann tensor is something that propagates with the speed of light, satisfies a vacuum wave equation, which is true in a wide variety of other theories of gravity. So in a wide variety of other theories of gravity, this statement remains true, that these guys, these 6 independent components here, determine all 20 components of the Riemann tensor. But in general relativity, 4 of these cease to be independent of the others. Only 2 of them are truly independent. So this is one reason that I'm going to focus on the components Rj0, K0, but I should remind you I'm doing this in a particular Lorentz frame. It's a Lorentz frame motivated by discussing a pair of particles and their motions. But this is not then, at this point, at this stage, a frame-independent description of gravitational waves. And I'm going to have to go back and elucidate what is the relationship to a frame-independent description in a few minutes. The second reason that I want to focus on these guys is that, in fact, these are the ones that show up in the relative motion of particles that are nearly at rest in a chosen reference frame. And that's precisely the situation you deal with LIGO and LISA, where for LIGO, these would be the test masses if you were to take LIGO and put it out in space, so you don't have to deal with the Earth's gravitational pull, which we will learn how to deal with perhaps on Wednesday, perhaps next week. For LISA, this is truly the situation for the proof masses that live inside the LISA spacecraft and that constitute the ends of the gravitational wave detectors, that they really are particles of just this sort. They really are very nearly at rest with respect to each other in the local Lorentz frame of one of the spacecraft. And so these are the components that are relevant for discussing things like LIGO and LISA. Now, to make the next stage in the discussion particularly simple, I'm going to define a new gravitational wave field. A gravitational wave field that is frame dependent. Everything I'm doing at the moment is frame dependent. That is a second rank spatial tensor, HJK, and on which I'm going to put superscript TT for reasons that will become evident later. So this is called the TT, or transverse traceless gravitational field. So TT, and you'll understand the reason for the phrase transverse traceless in a moment. And the definition is that Rj0k0 is equal to minus d squared hjk tt dt squared, and with a 1/2. And the 1/2 is, like so many conventions, is for historical reasons, but it also enables us to have a particularly simple equation later on in the lecture. So all I've done is replace the relevant components of the Riemann tensor, the ones that are relevant for LIGO or LISA. I've replaced them by something that differs from them by a couple of time derivatives. In other words, if you double time integrate the Riemann tensor at a fixed at the origin of this local Lorentz frame, then multiply by -2, you get my new gravitational wave field. So the two are completely equivalent. But the reason for doing this is so that the mathematics starts to look somewhat simpler in just a moment. In fact, we can now see how it's going to look somewhat simpler. Let's go look up here at the equation of geodesic deviation for my two particles or proof masses. It says d squared, the perturbation in the coordinate position of particle B as it wiggles under the action of the gravitational wave, is equal to minus the Riemann tensor. So this minus sign and that minus sign up there cancel, and I get 1/2 d squared hjk tt dt squared times the unperturbed coordinate location of my particle B. Well, it's easy to integrate this, and my integration constant is determined by the fact that I asked that before the gravitational waves arrive, the two particles are at rest with respect to each other. That was just for simplicity. You can always throw in another integration constant if you wish. And so the bottom line then, if I integrate this with that initial condition, is simply that delta xj is equal to 1/2 hjk tt times the coordinate position, the unperturbed coordinate position of my particle B. So that's a very simple relationship. And I now want to explore what it says. But in exploring what it says, I first want to tell you some properties of this gravitational wave field, of this frame-dependent gravitational wave field. And properties of that, of course, are equivalent to some properties of the Riemann tensor. The properties of this are as follows. For simplicity, let me orient my coordinates so the waves propagate in the z direction. Then I have that hjk tt is a function only of t minus z. These are plane gravitational waves. They propagate with the speed of light, as we know from the wave equation that the Riemann satisfies. And so something that propagates in the z direction with the speed of light is a function just of t minus z. The speed of light I've set equal to unity, remember. So it's some function of t minus z, and the properties that I'm going to have you prove, again as an exercise, again following from the Bianchi identities and vacuum Einstein field equations and the symmetries of Riemann. The properties are that the only non-zero components of this gravitational wave field are hxx tt, hyy tt, and hxy tt, which is equal to hyx tt by symmetry. And moreover, the trace vanishes, that is hxx tt plus hyy tt is equal to 0. The first statement says that these waves are purely transverse. The only components are in the x and y directions. There's no component whatsoever in the z direction. And the second statement says that this guy is traceless. And that's the origin of the TT, transverse traceless notation here. So again, that's something for you to prove as an exercise. But that then exhibits the fact that there are really only two independent components of the entire Riemann tensor. The full Riemann tensor is determined by the space-time components. The space-time components are determined entirely by this transverse traceless gravitational field, and by the transverse traceless properties, the only non-zero components are these three, which have one relationship among them. And so there are only two non-zero components. Those two non-zero components, it is conventional to give a simpler notation to, once I have gone to this special coordinate system. I will call H plus HXX TT, which is also equal to minus HYY TT. And I will call H cross HXY TT, which is the same thing as HYX TT. And of course, H plus is a function of t minus z, and H cross is a function of t minus z. So now I want to go back and look at what the equation of geodesic deviation says about the influence of H plus and H cross. So here is what it tells us. It tells us about the perturbation in the position of particle B induced by the gravitational wave. Let's look at the influence then of H plus. On the particle. I remind you again, this particle would be one of the two proof masses of LISA along one of LISA's arms, the other one being here, or if LIGO were out in space, it would be, say, the end test mass of LIGO, where this is the corner test mass. So delta x for the x component, so if I let j equal 1 or j equal x, is equal to 1/2 hjk, 1/2 hx x tt times x, the unperturbed x, plus 1/2 hxy tt times the unperturbed y. This is absent in the case of the plus component of the waves. And this I is just equal to h plus. And so delta x is equal to h plus, which of course is a function of t minus z, times the unperturbed x position. And similarly, one can go back to that equation and see that delta y is h cross times the unperturbed y position with a minus sign. I'm sorry, h plus with a minus sign. And the reason is that the same argument would go just replacing x by y, but hyy tt is minus h plus, so that's where the minus sign comes from. So it's the trace-free nature of this gravitational wave field that gives you that sign flip. In terms of a diagram then, what this says is the following, that if I had my particle A here, and if I put particle B right there, and suppose that H plus is momentarily positive, then particle B is going to move from where it began outward to here, say, through a displacement delta x, which is h plus times x, times the unperturbed x. If the particle was down here, then its initial x is negative, and so the displacement is negative, and the particle will move out to there. If the particle is initially up here, then it's at a positive y, and h plus is positive, and so it moves with a delta y that's negative, so it moves down like this. And if the particle is initially down here, then similarly it moves up. And so in fact, if I had a ring of particles that initially were on a circle like this, then after the wave has passed, this ring of particles will now be on an ellipse that is squeezed in that direction. And at the next half cycle, this initially circular ring of particles, because h plus will just flip sign at the next half cycle, it's going to be on an ellipse that is elongated in the opposite direction. So as the wave passes, an initial circular ring of particles will alternately get stretched horizontally and squeezed vertically, then stretched vertically and squeezed horizontally, where I've chosen the z direction to be into the board. You notice there is no stretch or squeeze along the z direction at all, and the particle's location, if you have a test particle up here, the test particle location in the z direction has no influence at all on the motion. So there's neither a delta z nor is there an x0 appearing in these equations. In that sense, then, the waves are absolutely transverse. If we look similarly at the influence of h cross, you can go through the same little calculation and get delta x is equal to h cross times y unperturbed. Delta y is equal to h cross, no sign flipped, times x unperturbed. And you can go through the physical meaning of this and see that what is going on is that a circular ring of particles around particle A will, when h cross is positive, it will get deformed like that, and when h cross is negative, it will get deformed like this. So these are just the deformations that I talked about in the initial PowerPoint presentation at the beginning of the course. Yeah.
There's essentially no difference between the two polarizations. I mean, they're just a question of how you define your axes.
So they're a question of how you define their axes, and so I'm about ready to discuss that. In fact, that's a very, very good point. But before I discuss that, I want to identify one other way of talking about this. And the other way of talking about this is to go back to the equation in this form. So that equation says then that the perturbation, or it says that the acceleration of particle B, that is the second time derivative of the position of particle B, is equal to 1/2 hjk tt times the unperturbed position of particle B. And that acceleration, of course, then can be thought of as the gravitational wave force per unit mass that acts on particle B when you think about the physics from the point of view of the local Lorentz frame of particle A. That phrase is very important. When you think about the physics from the point of view of the local Lorentz frame of particle A, then you can regard particle B as having a gravitational wave force acting on it. But if you take the point of view of Einstein, the original point of view of Einstein, both particles are falling freely. And neither one is to be preferred over the other one. And so it's only when you take A's point of view that B seems to have a gravitational force on it. When you look at it from the point of view of local Lorentz frame of A, if you look at it from the point of view of local Lorentz frame of B, then A seems to have the gravitational wave force on it. Okay. Nevertheless, this point of view is quite useful because, say, in LIGO, we will generally use the local Lorentz frame of the corner station in LIGO. Or we'll use a generalization to the case where it's sitting on the surface of the Earth, the proper reference frame of the corner station. And then we can think of the gravitational wave as exerting accelerating forces on the test masses in the end stations of LIGO. And that's a particularly useful viewpoint. Okay, so let me take that viewpoint where then particle B is feeling an acceleration or experiencing an acceleration as seen by particle A. It doesn't feel any acceleration at all. It's falling freely. Okay. If it's seen by particle A, it accelerates in this local Lorentz frame. And let's notice that this force is divergence free. As you see, because this will be 1/2 hjk tt, the partial derivative of xk with respect to xj, 0, which is the Kronecker delta. And that Kronecker delta just takes the trace on h. The trace is 0. Remember, I'm happily, cavalierly moving indices up and down because I'm in a Cartesian coordinate system. Okay. So the fact that this force is divergence free means that we can discuss it like we discuss an electrical force, which is divergence free. The electric field has vanishing divergence. In such a case, it's very nice to use field lines. Field lines that point in the direction in which the force points, and that have distances between the field lines that are proportional to the strength of the force. So you can just ask then, what are the field lines that you would draw corresponding to this force field? And the answer, not surprisingly, is for the H plus component, these field lines are field lines that stretch along the x direction and squeeze along the y direction. And so they're just like the field lines, like magnetic field lines in a quadrupolar magnet that's used in particle accelerators. And similarly, the cross component can be described by field lines that stretch and squeeze along axes that are rotated by 45 degrees with respect to the cross, with respect to the plus axes. Okay.